So this video is probably going to be in the general chemistry section as well as the first video in the orgo section, organic chemistry section, because they both cover this material, okay? So let's just go over what this outline talks about. So number one, the general definition of a bond. So a bond is the interactions of electrons in different atoms, usually different atoms, that cause them to attract and make a larger molecule. So there's different types of bonding, okay? And let's highlight this real quick. We've got intramolecular bonding and intermolecular bonding, okay? So we're gonna go through both of these. The way that I like to think about this, because I easily forget things, is intramolecular bonding is bonding within a molecule. Intermolecular bonding is bonding between two different molecules. Okay, so how do you remember that, Renee? Well, I remember that intrastate highways are highways that go through but stay within a state, intrastate highways. But interstate highways are highways that go and connect between multiple different states, okay? And so this makes sense that intermolecular bonding would connect different molecules, okay? Whereas intra is within the same, bonding, but within the same molecule. You're not going and bonding different molecules together. Okay, so let's look at the intramolecular bonding. So we've got covalent bonds, ionic bonds, and metallic bonds. So covalent bonds, let's put in a nice color here. Covalent bonds are bonds between a non-metal element and a other or the same non-metal element. So two non-metals, okay? In covalent bonds, electrons are shared. Now we're going to talk a little bit further down. They might not be shared equally, but they're shared. Ionic bonds, okay? So ionic bonds are between a nonmetal and a metal, okay? Now, I just can't help myself. I do want to talk about this. Is an ionic bond an intramolecular bond or an intermolecular bond? Well, ionic bonds, like in salt, we form a lattice work that could extend, forever, basically. So inside, for example, table salt, you have a sodium and a chlorine, and 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 a sodium and a chlorine. And so the bond between the sodium and the chlorine, right, extends in a lattice, okay? And so this bond, would you say it's within a molecule, one big lattice molecule, or would you say that's between molecules? Is each sodium and chlorine considered a molecule? Well, it's not really. The answer is you can't really call it a molecule. You can't really say it's within a molecule because you can break them. So, but for this outline, we're putting ionic bonds inside of intramolecular bonding because it makes a little bit more sense when you think of a lattice as a whole unit. But that's just me talking. That's not really important. Okay, but what is important about ionic bonds is that electrons are transferred. Transferred. Is that how I don't know if that's how you spell transferred, but that's my guess, okay? So what happens is an element has an electron, and if it loses the electron because it gives it away, right, it's transferred it to the other atom, okay, then that element becomes the cation. The cation, right? Electrons are negative. So if I give something negative away, I now become positive. and so I'm the cation. While the element or atom that gains the electron becomes the anion. Okay, so you've, for example, sodium and chlorine. Okay, sodium is going to give an electron to chlorine, and so now we're going to have sodium plus and chlorine minus. And so this sodium is the cation and this chlorine is the anion. Okay, now metallic bonds. Metallic bonds are also weird. Okay, they are just described as a sea of electrons. Okay, now let's move to intermolecular bonding. Do you remember what intermolecular bonding was? Bonding between molecules, okay? So, a very famous intermolecular bonding, hydrogen bonding, is very commonly confused, okay? Hydrogen bonding. So we're going to go over that, okay? To be honest, when I first learned about it, I was confused too. Okay, so typically seen when there is a hydrogen bound to a nitrogen, an oxygen, a fluorine, or a sulfur. But be careful, we didn't say that the bond was a hydrogen bound to a nitrogen, an oxygen, a fluorine, or a sulfur. We just said it's seen when you have an NH, an OH, an FH, or an SH, okay? But so let's dive into that a little bit more. Okay, so I'm gonna highlight that. Oh wow, that's really big. Let's try this again. So I'm going to circle this bond right here. Okay, see how we have an arrow pointed to it? And that says covalent bond. Okay, a lot of people think, oh, that's a hydrogen bond because it's going from the O to the H. It's really common to think that. And that's not true, okay? That is a covalent bond. It is a bond where electrons are shared, and it's within the same molecule, right? This O and this H are part of the same molecule. So the bond that connects them is inside of that same molecule, so it's intramolecular. But remember what we said hydrogen bonding is usually intermolecular, okay? Now, if we talk about biochemistry, it gets a little bit different, but that's, when we're first learning this, we're going to go in the most simple fashion, okay? So that is a covalent bond. The hydrogen bond is the association between the hydrogen of one molecule and the lone pair of the oxygen on a different molecule, okay? So here's what you need to know about hydrogen bonds, okay? To make a hydrogen bond, you need exactly two things. You need a hydrogen bond donor, and you need a hydrogen bond acceptor. Okay, so what are these? So the hydrogen bond donor is any molecule that has a significantly positive hydrogen on it, okay? How do we have a significantly positive hydrogen? Well, you can have a significantly positive hydrogen if you have an oxygen bound to a hydrogen, a nitrogen bound to a hydrogen, a sulfur bound to a hydrogen, and even, some people include a fluorine bound to hydrogen. Okay, so because oxygen, nitrogen, sulfur, and fluorine are all very, very electronegative, they pull the electron density away from the hydrogen, like this, and they make that hydrogen slightly positive. So now that hydrogen is sort of kind of positive, and what's attracted to positive? Negatives, right? So the hydrogen bond acceptor is just pretty much anything with a lone pair, because lone pairs are negative. So what's a hydrogen bond acceptor? A lone pair. Easy peasy, right? Oh, that's a lone pane, a lone pair. Okay, so notice here, this water molecule, we have a hydrogen that's bound to an oxygen, so that is the donor. And here on this oxygen, how do I know that that's a hydrogen bond acceptor? Well, the answer is very, very easy. I just say, hey, look, there's a lone pair. And yes, I have 2 lone pairs, but you only need 1 to do this, okay? Okay. So dipole-dipole. What are dipole-dipole bonds? So dipole-dipole bonds, they are another form of intermolecular bonding, and they exist between molecules that have a dipole in them. Okay, that's why they're called dipole-dipole. So let's look at this molecule right here. We have a carbonyl functional group, okay? Now this oxygen is very electronegative, and this carbon is not. So the oxygen's pulling electron density towards it. And what that means is the oxygen has a slightly negative charge, so slightly negative. That's what this delta sign means. The delta sign means slightly, and then the negative sign, of course, means negative. So let me draw that again. So the oxygen is slightly negative, and then the carbon is slightly positive, okay? Now, if we have 2 of these molecules next to each other, what can happen? Well, remember, the oxygen is slightly negative, and the carbon is slightly positive. And of course, you guys all learned in kindergarten probably that negative is attracted to positive. Makes sense, right? You all know that. You got that part down. So if this is slightly negative, then it's going to be attracted to, boom, 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 slightly positive. And so there will be an association, and we call that a dipole-dipole bond. Lastly, we have the weakest, which is a London dispersion force, sometimes also called van der Waals interactions. And this can occur in all atoms. And we can mention protein complexes here because London dispersion forces, the larger the molecule. Let me use this analogy. So London dispersion forces are the weakest intermolecular force. It's very weak, right? But if you have a lot of them all working together, they can become a significant force. So an example is Velcro. In Velcro, you've got one strip that has a bunch of little arcs like this, and then the other strip is just little hooks. So if you have one arc and one hook and you just attach them, you can break that off so easily. But usually in Velcro, we have a whole strip of them and multiple rows within that strip. And so when we put down the hooks, all the hooks that are on the top strip down, then you have to use significant force to pull it away. And the more hooks we have, right, the more attraction and surface area we have, the harder it is for you to pull away. And proteins are usually very large. And so there are lots of these very weak forces, but when you have a lot of these weak forces, the force becomes significant. And that is part of how proteins can fold through London dispersion forces, but that's not really going to be the focus of this section. So London dispersion forces, let me give you an example of what this looks like, okay? And we're going to use the bromine molecule, so Br2. Now if I draw Br2 out, we've got a bromine covalently bonded to another bromine molecule, right? So bromine bonded to bromine, cool. Now I might ask you the question, okay guys, do we have a dipole in this molecule? Well, the answer is no, because bromine has the exact same electronegativity as bromine, because it's itself, right? The exact same electronegativity means that the electrons in this covalent bond are shared perfectly equally, which means neither the left bromine nor the right bromine is slightly positive or negative because the electrons in between them are shared perfectly. But, let's see here, what can happen is if we have another bromine molecule, okay, we got two bromine molecules now. And let's say one of our bromine molecules is floating around, and it just happens to get close enough to our original bromine molecule, right? What's going to happen? Well, remember, there are electrons around our atoms. Okay, there's more than what I just drew. I'm just being lazy here. 1, 2, 3. Okay, and there's some around these bromines. Okay, there's more than what I'm drawing because bromine is very large. It has many shells of electrons. So there's a lot of electrons just in the area around the bromines. Okay, now remember, do electrons like other electrons? Well, no, because they're both negatively charges, and negative repels other negatives. So as this bromine is floating around and it gets closer to this bromine right here, boop, they're almost about to bump into each other, you have electron-electron repulsion. So what I'm going to do is I'm going to say, okay, blue is negative, negative-ish, and I will say green is positive-ish. Okay, so what happens is you have an induced dipole. So because this molecule is getting closer to this bromine here, the electron-electron repulsion occurs and all the electrons around here kind of run away. Right? They're like, oh no, electrons, and they sort of try to move away from those electrons that are getting closer to them. So what ends up happening is you have an induced dipole where this side of the molecule ends up being kind of positive-ish. Oh wow, that was bad. Kind of positive-ish. And this side of the molecule therefore gets extra electrons, so it gets kind of negative-ish. Okay? Now the funny thing is, because this side is now sort of positive, well, what's attracted to positive? Negative. So that means that this molecule here, the electrons are attracted to this positive side, and so the negatives try to come over here because they are attracted to this positive side of the other molecule, okay? And so if the electrons have moved to this side, then that means that the right side is now going to be slightly electron deficient because they all left to go to the left side. So that side is now positive, okay? So even though the molecule didn't start off with a dipole, when they got close enough to each other, they induced a very slight dipole. And that's where London dispersion comes from, okay? Alrighty, I think that's a good place to stop.